Welcome to the first lecture on Laplace transforms on NPTEL. Laplace transforms, the origins of Laplace transform can be traced back to the work of Leonhard Euler, who used it to solve some differential equations, but he didn't develop the theory entirely. And it also appeared in the work of subsequent mathematicians like Lagrange. But it was Laplace who really put his teeth into the problem and developed the theory quite a lot. And as I said, it was used to not only solve differential equations but also other kinds of equations like integral equations as well as difference or recurrence relations. So let me give a brief outline of today's lecture. So today we will see the definition of an integral transform, and next we will see that the Laplace transform is a special case of integral transforms, and then we will compute some first examples of Laplace transforms of some easy functions. And lastly, we will also review some theoretical background on what are called improper Riemann integrals, because the Laplace transform is defined as an improper Riemann integral, so it's useful to know what it is. And so we will see the basic we'll see some basic facts about improper Riemann integrals. So first, let us see the definition of a transform before we talk about integral transform. Let us see what are transforms. So a mathematical transform. So a mathematical transform can be described in pictorial form as a black box operation. Well, in this case it's a blue box. But let us suppose that on the left hand side this is our input, and the input goes into this black box operation, whatever mathematical operation it describes, and you have some output, and the middle is the transform operation. Okay, so let me denote the transform by t, and we suppose that in the input we get a function f of t. So ft is a function of with a real parameter t, and this transform t takes ft as an input. Now the output is another function which we shall denote by f with a different parameter s. So the transform changes the input or transforms the input ft into this output f of s. So in mathematical formulation we can write this as t of ft, and this is also denoted as fs, and this is equal to t of ft equals fs. So please edit out this part. So in mathematical formulation we can write this as an equation: t of ft equals fs. Okay, so it's obvious that this transform t should depend on this parameter s. Okay, so because it takes this function with a variable t and it outputs another function with the variable s. So this is our layout for what a transform should do. It takes a function and gives you another function. Now, what are integral transforms? So integral transforms are a special case. Integral transforms are a special case of a transform, and in this case t of ft is given by an integral formula, which is why it is called an integral transform, and this is given by an integral from t equal to t0 to t equal to t1 kst ft dt. So this is an integral where this kst is a function of two variables s and t, and we are integrating against t. So what we are left with is a function of s. Okay? So this is our f of s, and this integration can be performed on the real line from the points t0 to t1. Okay? Now we can allow t1 or t0 to be plus or minus infinity respectively. Okay. Now let us see some examples of integral transforms. Just a terminology, this function ks of t is known as an integral kernel of the integral transform of t. Okay, so this has a special name, it is called the integral kernel of t. So the first example can be given by the Fourier transform. This is a very well known transform. Fourier transform. In this case, the function kst is given by e to the power minus ist. Okay, and t0 is minus infinity and t1 is plus infinity. Okay. This is one of the transform. Here I is the complex number I, and kst is defined as e to the minus ist, and the integration is from minus infinity to plus infinity. Okay. So if we denote our transform, Fourier transform to be f, so I am replacing this t with an f, so f of t has the formula minus infinity to infinity f of t e to the minus ist dt, and this is our f of s. Okay. The second one is our Laplace transform, and in this case our integral kernel kst is given by e to the minus st. Okay, so just note that here there is a complex number I, but here there is no I. Okay, that is the only difference. Now let me say some words about this kind of formula, some motivation about how this formula can be thought of. So motivation for integral transforms. So if we take a matrix, an n cross n matrix, A11, A1n, An1, Ann. Okay. So this is an n cross n matrix, and suppose that x is a column vector, x1, x2, xn. Okay. So what is the formula for Ax? So Ax will be a column vector again, but I want to take the ith component of this column vector. So the formula is very easy. It is Aij xj j equal to 1 to n. Okay. So we all know this formula is the matrix multiplication formula, but if we just rewrite this formula as follows, where rather than writing ij as subscripts, I am going to write as ij in our function notation. So a can be thought of as the function of I and j two variables I and j, where both these variables are discrete variables, meaning that they only take values I and j, only take values between 1, 2, 3, etc. up to n. Okay. So this is a function of two discrete variables, and we can also think of this x as a function of this discrete variable j. So now if you compare it with the formula for any transform, integral transform, t of ft, which is t naught to t1 kst ft dt. So we see these two formulas are quite similar. The second one can be thought of as a continuous analog of the first one, meaning that this integral transform can be thought of as a continuous analog of matrix multiplication. This is just for an analogy, and this kind of analogy will not help us in our computations, but it's just to relate this formula with something well known, which is the matrix multiplication formula. Okay. Now let me talk about some motivation for the Laplace transforms. Here I am going to take what's called a power series, and by a power series I mean an infinite sum a(n) x to the power n. Here x is a positive real number and a(n)s are arbitrary real numbers. So n equal to 0 to infinity. So this is a power series, and usually when we have such an infinite sum, we talk of the radius of convergence of the power series. For example, let's see an example of power series where all the an's are 1. So in this case we have ax is just summation n equal to 0 to infinity x to the power n, but now this is just a geometric series, and this converges to the function 1 over 1 minus x, provided mod x is less than 1, right? So since we have already taken x to be a positive number, so this means that x lies between 0 and 1, and so this is our region of convergence for power series, given by an equals 1 for n for all n. Right? Now we can also take an to be 1 over n factorial. In this case, again we get something well known, x to the power n by n factorial. So sum over from n equal to 0 to infinity x to the power n by n factorial, and this is our well known exponential function. This is the Taylor series expansion of the exponential function, and this is valid for all x greater than 0. Okay? So the region of convergence is in fact the entire positive real number in this case. So this is the region of convergence. Okay. So now that we know what a power series is, I'll try to relate it to the definition of the Laplace transform. So let me rewrite this formula for the power series an x to the power n. Now we suppose that our x lies between 0 and 1. Okay. So in many cases we have only a bounded radius of convergence. So I suppose that this radius of convergence, this region of convergence is between 0 and 1. Now in this region I can make a change of variables by putting x equal to e to the power minus s, where s is positive. Okay. And because s is positive, e to the power minus s always lies between 0 and 1. So if we can write this power series now in terms of this change of variables, so we get n equal to 0 to infinity. Now again I am going to rewrite this a with a subscript n as a function of n. We suppose that a is a function of the discrete variable n, where n takes values between 0, 1, 2 and infinity, up to infinity. Okay. And here we have e to the power minus n s. Okay. So let me write this as Sn. And since we have now changed the variable on the right hand side, our dependency can be written as a of s. Now we are again in this familiar familiar formula. Now we are again in the familiar formula, where this is a discrete version of the integral formula that we wrote before, which was ft e to the power minus st dt. So here our f is just a, this coefficient function a, and our a is just fs. Okay. So this is the discrete part, discrete version, and this is continuous version. And of course this is our Laplace transform of the function at. So sometimes we will also write it as L of at. So note that here we have taken the limits of integration from 0 to infinity, but we can also allow minus infinity to plus infinity, and in this way we get two versions of Laplace transforms. First one is the ordinary Laplace transform, where the integral kernel is given by e to the minus st, and the limit of integration is taken from 0 to infinity, plus infinity. And the second is so-called two-sided Laplace transform, where the integral kernel is again the same, but now our limits of integration is from minus infinity to plus infinity. Now let me say some words about the uses of Laplace transforms. Laplace transforms can be used to solve linear ordinary differential equations, and it has the advantage that it can directly be used to solve such equations, and it doesn't require solving homogeneous equation first and then the inhomogeneous equation and so on. The other advantage is that one can have some singular functions like the Dirac delta function, which is not defined as a proper function, as inhomogeneous terms, meaning that it can be taken as on the right hand side of an linear ordinary differential equation, and one can still use Laplace transform techniques to solve such equations where other methods cannot or may not be used. So in the same vein, it can also be used to solve linear partial differential equations or systems of differential equations. It can also be used to solve integral equations and integral differential equations, difference or recurrence relations, and it also has applications in probability theory via the so-called moment generating functions. Except the last application, we will have the opportunity to learn about all the rest of the applications, how to solve linear ordinary differential equations, partial differential equations, systems of differential equations, as well as integral differential or difference or recurrence relations as well. Now let me say some words about the application to solving linear ODEs, for example. In this case, if we have an ODE, let's say y double prime minus y equal to t. So this is a linear ordinary differential equation. Now, normally we will solve it using some method, and we get the solution yt. Okay. Here, when we are using Laplace transforms, first we will transform this equation using Laplace transform. Into an algebraic equation. So we start with a differential equation and we get an algebraic equation. So this is of course much easier to solve than a differential equation. So we can solve it. So we get here an algebraic equation in the variable s, and here you get some fs. The solution for this algebraic equation can be written as fs, and now this solution yt and fs are again related via Laplace transforms. So if we know what kind of function gives you fs as a Laplace transform, then we can invert this arrow. So this is called the inverse Laplace transform. We can invert this arrow, and from fs we get back yt. So in this way, while we start from a differential equation, get an algebraic equation, we solve the algebraic equation and then take the so-called inverse Laplace transform to get our solution to the original ordinary differential equation.